Right. Okay. Sorry, everyone, for the little glitch. I'm very excited to be here to talk to you about the evaluation of generative models. And this is a topic that I've been digging for a while. Quite exciting. I hope you'll enjoy it. Okay. So this talk will be on particularly on evaluation of GANs, not models, because this is a big field, and there is not much time to go over all aspects. So I will uh, explain what is a good measure, what are the properties of good measures, and then from there I will go over quantitative and the qualitative measures. And lastly, I will relate to deepfakes and other aspects. Okay, so as you know, GANs have been very popular recently, and they have almost revolutionized the whole field. At the core of these models, there are two networks. One is a generator, which generates images, maybe other modalities, or maybe text, from a noise vector. And then these generated images, along with some other images from the data set, then are fed to a discriminator. Discriminator's task is to distinguish real images from fake ones. And these two networks are trained in tandem until they reach an equilibrium. At that point, then the network, the generator, is good to generate realistic looking images. Okay, and the loss function is a min max loss, which is basically, you probably have seen this, right? So you have this discriminator which has an objective function, something that looks like a, a cross binary cross entropy, right? So you repeat this, the training the discriminator for a couple of steps, and then you do gradient ascent here. And then after you're done, then you just go to the generator and then you do one step of gradient descent here. And the losses are actually pretty simple to understand. So the first one would be d of x. Basically, you want to maximize this. So this is basically, you want a good classification for real images. So you want the d of x to be 1, and then d of g of z, right? You want this to be 0. So you want to give label 0 to the fake ones. So 1 minus 0 would be basically, again, high, right? So that's the goal here. And at the generator, you want d this time to be 1, because you want to fool. Basically, you want to generate images such that this d of g of z becomes 1, right? So when you do gradient descent here, and then if you get that, if you get d of g of z 1, which means that you have basically tuned your generative parameters, then that's a good image, right? Good enough to fool the discriminator. And there are a lot of tricks to sort of make this network stabilized, which I'm not going to go over, but that's the core idea. Okay. So GAN evaluation basically, so sort of GAN or generative modeling in general is an instance of density estimation, and you've probably seen some methods here. There are two broad categories. One is non-parametric. You assume you have no form for the distribution function, and some examples are like histogram techniques, right? K nearest neighbor, Poisson density, which is basically in K nearest neighbor, you basically you basically grow a hypersphere until you get a certain number of neighbors. Conversely, in the Poisson window estimation, you assume a fixed window size, and then you just count how many neighbors fall in that, right? From these, then you can simply calculate, so you can calculate the density. The most common approach is kernel density estimation. As you can see here, you just place a kernel on each of your training data points. The kernel could be like a Gaussian, like here, it could be a rectangle, could be any shape, could be a triangle, and then simply you sum them up, right? So if you want density at a certain point, you just see how much activation you get from all other kernels, from all the kernels, and that's your density. Uh, Parametric methods, right? One is maximum likelihood, which is basically assume your data is IID, and then the probability of seeing all data is just simply the multiplication, right? So if you want to maximize this, you take the derivative of this, and usually before doing that, you take the log to convert exponents to sort of to remove the exponents, right? And that makes the job easier. And Bayesian estimation is the almost same, except here you assume you know something about your parameters. Parameters here are not, your parameter estimation is not point estimation like ML. Here you assume you want a distribution over these parameters, right? So P of theta it itself has a distribution, right? And so you assume a prior for that, right? So P of T of D, you want a distribution over T given the data. And solving this is again similar to the P of D, maximum likelihood. You do basically, you take the log and then take the derivative, and from there you go. And if you don't know anything about P of theta, right? So if P of theta is uniform, then basically this just reduces to the ML solution. And then there's this maximum expectation maximization, which is some sort of like a two-step iterative approach. So expectation followed by maximization and so on. And it's basically, uh, if you just to quickly go over, this is basically how k-means works, right? Basically you select some random points, so select some points as cluster centers, then you calculate distances to cluster centers, you update clusters, then again you do assignment, and so on and so forth. Okay, so and there are a bunch of applications for this, right? You can make a, once you calculate these densities, you can do Bayesian classification, outlier detection, or in this case that we're concerned, GAN evaluation. Okay, so GANs are unsupervised methods, unsupervised learning methods, right? And it's sort of difficult to evaluate unsupervised approaches because there's no ground truth, right? It's not like classification or segmentation that you know the ground truth. Here you have to sort of rely on some other approaches. So usually there are two sets of data. One is the generated samples, and the other one basically the real samples, if you see that on the figure on the top. And then you extract features from this for these images from a network, let's say inception network. And then basically once you get these two distributions, then you can sort of get the distance between two distributions, right? And in the following, I will talk about some approaches. And so you may think, if a generator just generates realistic images to a degree that a person cannot tell which one is real, which one is fake, then maybe that model is good, right? In other words, if the model passes the Turing test, which is not right, because the model could just generate few very good images and then just forget about the rest of the distribution, rest of the support, and uh, and that's not good. And that's in fact what happens in mode collapse and mode drop, right? So okay, so one thing to know is that the evaluation can be also task dependent, right? So depending on the downstream task, then different generative models could have different scores, basically, right? Uh, but what I will talk about are more some sort of like universal general measures. And two of the most important criteria are fidelity and diversity. Fidelity regards the quality of images. Diversity basically is concerned with how diverse is the set of generated images that you generate. And so in addition to these two features, fidelity and diversity, then there are some other desired properties that we wish to have a measure to have. So, for example, you may want the generator to have a disentangled latent space, such that the axis of this latent space corresponds to semantic dimensions, right? Maybe one, let's say, if you face generating face, maybe one sort of is aligned with age, maybe another one is beauty and things like that, right? So it's good to have a measure that has well-defined bounds, like a lower bound, upper bound, and chance level. So this makes analysis easier and comparison also. Also, you want the measure to be sensitive to image distortions and transformations. So if the generated images have low quality, then you want the measure to capture that. Also, you want these measurements to align with how we judge the images and rank the models. You want a correlation between human judgments and these measures, basically. Last but not least, you want these measures to have low sample and computational complexity, so they are easier to sort of to apply. Right? You don't need like gazillions of examples to just evaluate these models. So I've written two papers on the topic. Okay, so here is a list of quantitative measures, and I'm going to talk about some of these the measures that are highlighted in red. Okay, so the what the, basically you right off the bat you may think of like average likelihood to be a good measure, and this is good because it can easily show that minimizing the KL divergence is actually equivalent to maximizing the log likelihood. And this is good because then it means that you're actually sort of getting closer to the real distribution. But it has major problems, the average log likelihood. The first off, it's difficult to sort of estimate estimate this in higher dimensions, and because of cares of dimensionality, and maybe usually the intuitions break when we go to higher dimensions. Another aspect is basically this measure is not informative about the quality of the samples. And so you can have a good model. So if you have a model that is just like a lookup table that just memorizes some images, right? Then this model can have a very poor log likelihood, right? Because for the test images, basically probably zero, right? You just remember some good images, but it generates very good quality images, right? And conversely, you can also have a model that has very good likelihood but generates very poor images. So you see this mismatch basically. And so as an example here on the top right, so Tice et al, they basically they fitted a Gaussian to 6x6 image patches from CIFAR, and then they try to estimate this Gaussian with Parsons window, and you can see with even too many samples, a lot of samples, they were not able to get close to the real log likelihood. So basically that's not good, right? So it's hard to get to the real log likelihood. And also, as shown at the bottom, you see that like a model, like a k-means model, basically your generator is just a k-means, right? So you cluster your images, in this case MNIST images, and then you just sample from the cluster centers, and this model gives you a better log likelihood, even better than the true distribution. Okay, so these are the, due to these problems, average log likelihood has not been adopted much in the literature. So one of the popular ones is the inception score, and this is basically based on the inception V3 model. Yeah. And as you can see here, this is the KL divergence between two distributions, one conditional distribution, probability of y given x, which means that basically what is the decision of the classifier for your input, which is generated image, right? And then probability of y, which is your marginal distribution, and this is over all the generated images. So everything happens over the generated images. So P of y is like your average distribution over all the generated images, and Py given x, you're looking at one generated image, right? And now you want this to be the KL divergence between basically this, right? And so if KL divergence is high, then it means that you're generating your generator is good. Why? Because to maximize this, basically it means that Py has to be maybe here, right? Your Py has to be uniform, and py of x given x has to be peaky, right? So just like an impulse function, let's just say, right? So right, so what it means now, if py is uniform, then your generator generates diverse set of images, right? So you guarantee the diversity. And if this is peaky, py given x is pointy, it's peaky, right? Then it means that these generated images are good, have good quality, such that they are easily classifiable, right? And that's the idea basically here. Okay, and there's this illustration here, for example. So if you generate images from all the classes in ImageNet, your marginal distribution would be uniform. And then if your images are realistic looking, then this will be basically just like one like peak, and then that's good, right? So the lower bound is 1, the upper bound is the number of classes, or you can use real images to approximate the upper bound here, because everything, as I said here, is just using the generated images. Okay, so this score has a reasonable correlation with the quality and diversity of the generated images. The problem, though, is that it can be easily gamed. So if you have a generator that just generates an image, just a single image for each of the 1,000 classes of ImageNet, then your marginal will be flat, right? Which is good. Then your images are also very good, because this is like training images. Then you basically can get a very high inception score, right? So it cannot basically address memorization. And so it only considers the fake images. Some scores have tried to remedy this by factoring in the real images. And it's not sensitive to mode collapse. And maybe the biggest problem is basically this score is biased towards ImageNet. All right. So if you're an inception model, so if you're generating faces if you want to evaluate the face generation model, then maybe this score is not appropriate. And so yeah, as I was saying, this is sensitive. IS is sensitive to image resolution, and so some scores, let's say look at the AM score, for example. Now they have also included the probability of basically labels over the training set. So you see the KL divergence between py train and also so this basically guarantees the diversity here. Now what it means that you want to generate all the images basically in the train set. You don't want it to be uniform, but you want it to be closer to the distribution of all the labels in your in your data set. Okay, and then the second term in AM score is as inception score, which basically guarantees sort of entropy. Okay, so if a distribution is pointy, it means it has low entropy, basically. Okay, so to remedy problems of inception score, then people came up with the Frechet inception distance, FID, and this is basically in this score you basically assume a Gaussian distribution over inception embeddings. So you get embeddings from the inception model. You feed the multivariate Gaussian distributions to these embeddings, one for fake images and another for real ones. And then basically you just put it in this equation, which is shown on the right side, which is basically you measure the distance between the means and the variance in the univariate case, or or basically covariance in the multivariate case. Okay, so that's the idea. Now the lower the better. The lower bound is 0 here. The good thing is it has nice properties. It can be used to monitor the progress during training, because you can just have one set of images, real images, right at the beginning. You keep it fixed, and then as you train the model, then you get another set after a while. Then you use that to measure FID, right? So for the real images, you just need to calculate the embeddings once, and that makes it economical, sort of. It is sensitive to mode collapse. Problem is you need a large sample size for this score to be meaningful, usually around 50,000 fake and 50,000 real images. And so another problem is that typically FID is lower for larger sample sizes. So if you increase the sample size, you can manipulate the FID to go lower, right? So that's one way to sort of to exploit this score. Another problem is that it only considers two moments of the distribution, and disregards higher moments. Just like inception score, this score is also biased towards ImageNet, right? Which is not good. And here you see FID is sensitive to Gaussian noise, Gaussian blur, right? So FID lower is better. As you see, if the image is disturbed, then the FID goes higher, which means the model is not doing well, right? So just like OIS, again, there are some variants of inceptions of the FID score to remedy some of its problems. Okay, so if you look at this figure, then you see that FID indeed encodes fidelity for a model. The right side model generates much more realistic images than the one on the left. Okay, because the FID lower the better. Does it encode diversity? Here's an example where the answer is yes. So the model on the right gets much lower FID from the one on the left, which generates almost sort of similar looking images. Okay, so good. It encodes both diversity and fidelity. But here is an example where there are two models that basically have about the same FID, but one has basically generates more diverse images, the one on the right, but maybe less realistic, whereas the one on the left generates less diverse images, but more realistic ones. So you see the problem here, right? So having just one score is maybe it's good, right? Because then it's easy to compare models. It's a good summary, but the problem is then it convolutes different things, right? Maybe it would be better to sort of have these two aspects separately, and then see basically then it helps you to analyze the model, just like we have, let's say, precision and recall to measure performance of classifiers. As a matter of fact, precision and recall has been also proposed to evaluate generative models. Here, if you look at the image on the right, then precision is first P sub R and P sub G are distributions of real and generated images respectively. And now if you want to calculate precision, basically precision is true positive, which are the red dots, or true positive and false positive, which is all these points that fall in the generated region, right? So if some of these points fall off the real manifold, and those are the images that they don't look realistic, like this ping pong ball slash chicken, right? And so if the two distributions completely overlap, then your precision would be high, and also your recall. Recall, on the other hand, is basically true positive or true positive plus false negative, which is basically again overlapped region uh, over the data points that are in the real data set. And this one basically tells you which ones the model is missing. For example, this donkey or the car, right? So these are so recall sort of encodes diversity, right? It tells you which ones the model is not good to capture, whereas precision relates to fidelity, right? So if model generates not the realistic images, then it will score a lower precision. And there are some variants of this score as well. So to calculate precision, this is an illustration. So you basically, let's say for k equal 1, like one neighbor, nearest neighbor, then you sort of have this sphere. You grow the sphere over each real image until you reach one neighbor. Let's say here, right? This is this is the sphere around this that includes one nearest neighbor. This is another one. This is another one, and so on, right? And now you look at your fake samples and count how many of them fall in the real manifold. So now from these 6 points that are shown here, 2 of them indeed happen to be in the real manifold, right? And now your precision is just 2 over 6. Okay. If you calculate recall, then you do the opposite. You basically consider, let's say K1 in this case again, and and then you count how many real samples fall in the fake manifold this time. Now, if you look at this example, there are 9 real samples. 7 of them happen to be in the fake manifold, so your recall is 7 over 9. Okay, so that was precision recall, which basically you separate precision diversity from fidelity. Another score that came out with the style gun is called perceptual path lengths, PPL, and basically, so what this score does is to sort of to tell you how entangled is the latent space. And intuitively, it's basically if you look at the figure on the right side, is as follows, right? So you consider 2 latent vectors, let's say z1 and z2, and then basically you look at the generated images for these, and now you do interpolation, right, along a line connecting these two, and then you pick a random point, let's say t here, right, and then you look at the point right next to it with an epsilon, let's say, and then you basically look at the generated images corresponding to these 2 vectors, right, and then you measure the distance between 2 images, and then you repeat this for different t's, right, and then take the average distance. Okay, now, so let me repeat this again in case it's not clear, right? So you take basically 2 random latent vectors, z1 and z2. Then you take a random point along the line that is connecting these 2, right? The interpolation, basically it's interpolation, linear interpolation. And then you look at nearby points, a nearby point around this point, t and t plus epsilon. You generate images corresponding to these 2 latent vectors, and then you calculate the distance, basically. Okay, and then you repeat this for many t's and many z's. On average, you get an average distance. And right now, if you have a model that has this sort of a smooth latent space, then its PPL would be lower than the one that that doesn't have a disentangled latent space. An example of that is shown on the bottom right. So this model, for example, right? So basically, along an axis that generates dogs, out of sudden it generates a bunny, for example, right? So and that causes the distance between these images to be very high. Okay, so that's the idea basically. And here's an example. You see that panel A, it's a model that has low PPL. The lower the PPL, the better, because it's distance, right? Whereas the model on the right has a high PPL. And as for the distance, then you can use any distance, but there's this distance called learned perceptual image patch similarity, and that comes from an image net that has been specially trained to sort of to capture the judgments of humans. Okay, so the embeddings from this, you can use the embeddings from this and then calculate L2 distance, and that's basically perceptually more meaningful than just the Euclidean distance. Here is an example that there are two models here compared. The FID, precision, and recall for these two models are about the same, whereas the model 2 below basically scores a much lower PPL, and it looks like it generates much better images from the top that has a much higher PPL. Okay. And so one quick point here is also the effect of sampling. When you generate images, right, at the inference time, test time, you can basically truncate your the distribution that you use to sample the latent vector, right? So if you look at the bottom image, right? So you sort of discard the flanks of this Gaussian, and then what happens is then you will get images with more fidelity, because that part of distribution has been seen much more during training. Okay, so this, you can use this to sort of to tweak the score, right? You can see, for example, this can help precision, right? Because precision encodes fidelity. And also for your applications, maybe you don't care about diversity much, you can just sort of train, you can tune this truncation hyperparameter for your need, basically. Okay, so another score. So those were the most popular ones, but there are some other ones that I'm just going to quickly go over to give you some ideas about like what people have been thinking in this field. So one is classifier two sample tests, and the idea is this, right? So you want to know whether two samples are come from the same distribution or not. So your null hypothesis is that they come from the same distribution. And what you do is basically, so let's say in our case, right? So we have fake images, real images, and then basically you give label, let's say 0 to your real images, and fake. So you give 1 to the real images and 0 to the fake images. You put them together, the data set, right? And then you shuffle the data set, you carve out a training set and a test set. Then you train a classifier, a binary classifier on the train set, right? And then test it on the test set. Now, if these two sets were not separable, then you would expect to get a score about the chance level, 50%, right? But if you get a much higher accuracy, then it means these two distributions were separable in the first place. Okay, so this is the idea. So if they were so these fake images, if they were not really separable, right? Assuming the classifier does a good job, is a good classifier, then if your performance on the test set is not better than chance, then it means that yes, they were not separable. But if it was higher than chance, it means that the fake images maybe are not as good as the real images. Okay, so that's the general idea here. Another score is classification accuracy, and here the idea is basically you train an image classifier on synthetic data and then use it to predict the labels of the real images. Okay, so the advantage of this is that they basically then you can tell which classes the generator is not doing a good job. Okay, and similarly, there is this score called FCN, which is basically for evaluating, let's say, conditional models like pix to pix. So let's say you start with a segmentation map and you generate an image, right? Now you can segment this generated image and see if its segmentation map matches with the conditions segmentation map. Okay, so that's the idea. So another one is called birthday paradox. I'm not going to go too much about this, but this is basically, actually, let me just skip this one for the interest of time. Another score is generative adversarial metric. It's called GAM. So here you have basically the way it works is just pairwise comparison. Let's say you have model M1 and M2, right? You train each discriminator with respect to its own generator, right? And then at test time, you swap the generators. So you basically match D1 against G2 and then D2 against G1, right? And see which one wins, right? So if basically if G2 can fool D1 better than G1 can fool D2, then maybe G2 is a better model, generative model. Assuming, again, the big assumption is that one model does not completely basically override the other one, right? So if the discriminators have about the same accuracy, then you can do this comparison. And now if you have n models, then you have to look at all over pairwise comparisons to come up with a ranking, which makes this score sort of expensive. There are some measures based on image quality borrowed from image processing literature, like SSIM, PSNR, sharpness difference, and such. Okay, so similarly, there are some methods that analyze the spectral properties of the generated images in the frequency domain, right? And if you look at the top right image on the left panel, what you can do, you can take the spectrogram distribution, like this, the frequency plot for each image. Then you can look radially, right, and take the from the center, just go outward, and then along this radial circle, you take the distribution, right, and then it will give you this sort of curve, right, from the lower frequency to higher frequency. Now, if you do this for many images, generated images, and take the average shown on the right side, you see that the real images, it just smoothly goes down, but for generated images, you see this sort of peculiar region at the very end. So it sort of generates some high frequency noise sometimes. Okay, so and that's some sort of an indication that you can tell whether an image, whether this is a fake image or not, right? So this is shown on the bottom, right? So for example, so this is the average spectrum over the FFHQ dataset, face dataset. And on the very right side, you see the same, but for the generated images. Not sure if you can see, but there's some like outlier points there, right? So this, knowing this, the people have used this as a regularization term to improve GANs, and also some others have built detectors to identify fake images and videos. All right, so that was about it for the quantitative measures. As for the qualitative ones, then there are few, and so one is the nearest neighbors, and the the idea here is basically to traditionally to sort of to tell whether the model overfits to the training data or not. Then alongside every, like some generated images, people show the nearest neighbors. And the problem with nearest neighbors, especially using Euclidean distance, is that if you just simply shift the image, right, one or two few pixels, then the L2 distance is dramatically different. So you can in fact find another image which is completely different than the image that you're looking at, but has a lower Euclidean distance with the shifted versions of this image. Okay, and that's the big problem with that makes it difficult to sort of rely on this analysis. Maybe for like to just visually show something, yes, but sort of to rely on it, not much. But if you use maybe if you do Euclidean distance on some, let's say, sort of embeddings that are more meaningful, right? Then it alleviates the problem using the pixels a little bit. Another approach is to sort of to show the images to people and ask the people to tell you whether this image is real or fake. Okay, so it's shown on the right side, and this is some sort of like a Turing like a test. Okay, and ideally a model is better if people report a higher percentage of uh, real, right? If they classify images more as real. There's a small problem here, because if you show all the time just generated images, very early on, subjects may notice that these images are coming from a model, and from then on, then always they say fake, 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 fake. Better way would be just to sort of to shuffle the data and throw in some real ones. Okay. Similar to that one, there's this hype measure, very similar. There are two variants of this. One would be basically time that tells, okay, an image is better, right? The fake image is better if it takes people longer time to identify it as fake. Okay, so they progressively grow the presentation time, and then see at which point people are able to distinguish the image. Another version of this is called hype infinity, and that's basically they discard, just like the previous slide that I showed. They don't care about the presentation time, they just want to know how often people classify images as real or fake, just the percentage of reports basically. Some measures they to probe generalization and also mode drop and collapse. So what one thing that you can do, you can sort of start with distributions for which you know some features. For example, here your images are have some, let's say, 2 3 circles, squares in them, right? For example, you know your training data, you generate your training data such that they always have two, or whatever, that you know that, right? So in this case, they always have, let's say, the bottom figure, they always have two. But then you look at your generated images, then your distribution has multimodals now. Maybe sometimes it gets 1 2 3 or so, right? This way you can sort of, with using the synthetic distributions, you can tell something about generalization of your model, or mode collapse. Extension of that is shown here for mode collapse. For example, here, this study, so some Turker et al. So they train again unconditionally on some balanced multi-class data set. So you start with a balanced data set, multi-class, right? Same number of instances per class. Then you train a multi-class classifier on this train set. Now you train a generator on this data set and use this classifier that you have to classify your generated images. Now, if you see that, again, you look at the distribution that you get, right? The distribution of classes. If you see that's also balanced, then it means that you're covering all the modes. Maybe if you look at the bottom figure, right? So the true has this flat uniform distribution, but if you look at the ALI model, for example, maybe that's a better model because it sort of has a flatter, whereas WGAN maybe is not good because it drops the kitchen example in this case, right? If you look at the top figure, then you see your true distribution are a bunch of Gaussians, right? The true data distribution. But if you look at ALI model, again, maybe it collapses all these modes to just one, but some other models are doing a better job, okay? So this is like using synthetic distributions, you can study mode collapse and mode drop, basically. Similar to that here, what they did, Bao et al., basically they, so you get the, you segment the training data, right? You do segmentation, and then look at the distribution of segments that you have, right? And then you do the same thing on the generated images, and then compare these two distributions. So if basically you see a big difference in some of the classes, then it means the generator is missing some aspects, right? So this is one way of doing that. In fact, they actually went deeper. Their method also sort of, you can do it in instance level. They are pretty nice demo of this that you can sort of add, knowing like what neurons are irresponsible in the GAN for some classes, then you can sort of add a person, remove a person, add three, and things like that. You can do fine-grained image editing. And so just like the PPL, maybe similar to that here, this approach, GAN steerability, basically tries to understand how, again the disentanglement in the latent space. And the way they do this, basically they say, basically they take if you look at the equation on the top, they take a z vector, right? They generate an image, they generate an image for it, correspond to it, and then they edit that image. Let's say the dog example here, right? Say, okay, I'm going to basically scale this image, right? And then they say, okay, let me find a direction in the latent space such that basically the linear transformation of this z plus alpha w, right? You want to find this direction such that if you walk along that direction, right, then you basically, the images that you generate, the distance of those with the edited versions that you manually generate, you want that to be minimized, basically. So let's say if you want to do scaling, right, so you walk in a direction that basically does the scaling for you, okay? And once you find this direction, then you can do the same thing for some for generated images. You can do the same thing for the real images, right? By editing, and then you get two different distributions that you can actually you can get two distributions, and these distributions are like the features in these images, right? So we say if I scale my images or rotate my real images, this is a distribution that I get. And now once you do this optimization, you solve this, right? Then you say, okay, this is the scaling or rotation in the latent space, right? And then you get a distribution of features there, and then you can compare these two distributions, basically. Okay. So naturally, GAN evaluation or generative evaluation of generative models sort of relates to deep fakes, right? Which is becoming a big issue recently. And so here's an example that basically by visually inspecting the images, you can identify some fake images, right? If you look at, for example, here, if you look at some glitches around the lips, corner of the glasses, for example, details are like that. Most importantly, the background, right? You see these peculiar things are generated in the background, and these cues you can sort of use to tell whether these images are real or fake. And this is exactly what we talked about, right, in these qualitative measures, that you can sort of so people that are building fake detectors, they are actually sort of also developing some sort of measures for GAN evaluation, right? And so the difficulty of like being able to tell which one is fake or real is also class dependent, right? Faces are maybe harder for us to tell, because generator usually, like, the generators work with these images that are calibrated, right? Eyes are sort of, when in these data sets, right, eyes are more or less about this in the same place, whereas for cats or dogs, right, or bedroom, it's very difficult to sort of calibrate images, and makes it image generation more difficult. Consequently, makes it easier to tell which ones are fake or which ones are real. Okay, so just recently I came across this model, this paper, that they inspected the iris, right? So the iris in humans is actually quite circular, but the generated images, you see, this
Sorry,
has this
Dr. Borji.
yeah.
Sorry, Dr. Borji. We have a few minutes to start the next lecture. Please finish your talk
Yeah.
that we
So
have
I'm
Q&A
yeah,
session.
yeah, I'm
Yeah.
almost done. This was just yeah. So now you can just look at this and tell me which, just for yourself, right? See which ones are real or which ones are fake, right? Very difficult. Usually background is a good cue that you can distinguish from fake ones from real ones. For cats and maybe bedroom, other categories is harder. And in fact, there's this website is called This X Does Not Exist. I encourage you to go there and see the images for yourself. All right, so that's about it. So I gave you a quick rundown of evaluation measures for GANs, and some measures like inception score, FID, PPL, and precision recall are more accepted and are adopted more frequently than others. I skipped some measures based on the statistics of natural images. So natural images have certain statistics like distribution of edges and such that you can use to sort of compare, generate fake versus real images. Some measures that they consider the geometry of the latent space, and some other. Okay, and also two other aspects that there was not much time to go over were sample complexity and sample efficiency and computational efficiency of the scores, basically. So for future, I think it would be interesting to sort of uh, to extend these ideas for, or come up with measures to evaluate text generative models, video, audio, and maybe tabular data. Now, knowing which scores are better than others, we can do like exhaustive model benchmarking, or even benchmarking measures. And it would be nice to sort of to see how this field also relates to sort of generalization of deep learning models in general, and in particular to adversarial examples and deepfakes, and not to forget also bias and unfairness in this field as well. And thank you very much. That was it for me.